I'd like us now to walk through how to actually calculate a linear regression using Excel. For the purposes of HCD 501, what I'm really interested in your ability to do is interpret the regression model output, but sometimes it's helpful to know where that table came from. So let's do that right now. So I'm using the data set for our linear regression example that you've seen in the lecture from this week, where we're interested in looking at the association between the high temperature for the day in Phoenix versus the number of heat-related emergency department visits that day in Phoenix hospitals. Um, so what we do here is we have this nice data set that's been prepared for us, and we can see it goes from June to the end of August, and we have the number of heat-related ED visits here in column B. That will be our outcome variable, or outcome of interest. And for the simple linear regression model, we have here in column C the daytime temperature. So for those of you who live in Phoenix during the summers, these will look familiar to you. For those of you who are from other parts of the country, these might be a little bit jarring, but yes, it does get to be 115 or higher. So there are ED visits that happen because people just get too hot wherever they're either inside or outside, and sometimes it's helpful to be able to know what that association actually is. So we will use the data analysis tool pack in Excel. We use the regression tool, and let's fill in our data right here. So our Y range, looking back to the lecture material, we know that Y is our outcome of interest. So that's here in column B, the number of heat-related ED visits. Our X range is our input, our predictor of interest. So that's here in column C, the daytime temperature. Our output range, I like to keep it close to the data. This is a personal preference. You'll notice that I have here checked the labels box. That's because I have the input range from C1 through C93. So that includes this label here. That's a personal preference. I just like it because then Excel will automatically put that label into the output table. It just makes it a little bit clearer to know what's going on. I also selected the 95% confidence interval just to get those pieces of information as well. So now we hit OK, and what do we come up with? We come up with a table where Excel has calculated the linear regression model on our behalf. I'm going to make this a little bit easier to read here. And we see that we have 92 observations. We have an R-square very, very, very close to 0. We have an intercept that is 100 and call it 119. So that means that if the temperature was 0, if the X value in our regression was 0, we'd see an average of 119 ED visits. And we can see that the coefficient for temperature is negative 0.0003, or 3/10,000ths of one ED visit. So essentially more or less 0. We see here that the p-value for that is 0.99. That's just about as high as a p-value can get, very, very close to 1. So from this model, what I would interpret is to say that there's absolutely no association between the temperature, the high temperature in Phoenix, and the number of ED visits that occur that day. But if you remember from the lecture this week, one thing I warned against is rushing to the regression. And so I actually put a little bit of a hiccup in these data, and this is not, I created this one, but this is by no means unusual. I do a lot of work with data on spending, and it's hard to overstate how often it happens that somebody misenters a comma or a period, or enters their data in thousands instead of in individual units, and you end up with weird stuff that happens. So this is actually a bit weird because you wouldn't expect that as temperature goes up, the number of ED visits goes down. Even though that's not a significant relationship, it's still not what I would have expected to see. You'd expect that as the heat gets higher, there are more ED visits, not less. So let's go down and look at our temperature column here. Perhaps the easiest thing to do would just be to look at descriptive statistics for this variable. And I'm going to do that just by highlighting this column. There is a label in that first row. Let's put the output here. We want summary statistics and a 95% confidence level. So we can see here the average daily high temperature is 117. Again, for those of you who live in Phoenix, that's not out of the realm of what we've experienced, but it is a little bit high. That the average temperature for the summer generally isn't 117, but you know, it's close enough. But the median is 107, and that matches my experience, at least for the last several years. The most common is 111. Again, not out of the realm of feasibility, but the standard deviation is 102 or 103. That's really high, right? Our range is 994. So there may be something going on here. The minimum value in the data set is 96. The maximum is 1090. I can promise you it wasn't 1090 degrees in Phoenix over the summer, so let's see what's going on here. And actually we can see right here, just so happens that according to this data set on July 8th, there were 113 ED visits and it was 1090 degrees. Just looking at the data around this day, it sure looks like that may be a data entry error, and specifically it's very feasible that we just added another 0 there at the end. So I do not recommend doing this as a general practice, but just for our purposes right now, let's recalculate this, assuming that it was actually supposed to be 109 degrees. And I haven't told you the year these data come from, but if I did, if you were actually doing this as part of your job, I would expect you to go back to historical weather data to confirm that it actually was 109 degrees on July 8th and not 1090. So now that we have that, we can recalculate our descriptive statistics. And suddenly this is looking a lot better. Now our standard deviation is only 5 degrees, and that is much more reasonable. Our mean is 106.5, our median is still 107, and our mode is still 111. Notice those didn't change. And our maximum is now 118. That makes a lot more sense to me, even though it is still very hot. So again, I said don't rush to regression. That's one of the things that can happen if you do. So now that we've squared up that, let's do another look at the regression model. And again, we're keeping all the inputs the same here, and it'll give us a little overwrite warning message. And now we can see some pretty different data here. And we can see a couple of critical things are that the p-value for the temperature variable or temperature coefficient is 0.00. You can see it's actually a lot of zeros. It's extremely close to 0, which means it's definitely less than 0.05, which means we can reject the null hypothesis and conclude that there is an association between these two variables, between temperature and number of ED visits. So here we can interpret this this way. For each 1 degree increase in temperature in Phoenix, there are about 2.46 it's associated with about 2.46 more visits to the emergency department across all of Phoenix. And that relationship is significant. We can then interpret this intercept to mean that if the temperature were 0, we would expect there to be negative 142.49 visits to the emergency department. Now obviously that doesn't make any sense conceptually. You can't have negative visits to the ED. But this does suggest that there is a temperature at which you wouldn't have any visits to the ED, and that as temperature increases, there may be an association with more ED visits. That makes a lot more sense than what we said before. So that's how we get this summary output table that that's shown in the lecture this week, and we can go about interpreting it as the lecture says.